another event for us, chapter Toronto. And so before we start, we have few stuff. Pizzas. Please grab pizzas before he starts speaking. And another thing, housekeeping. When you're done with eating, please make sure you throw the stuff away. And yeah, a washroom. Washroom's gonna be a bit tough, so you have to go all around the security, go around security till the end. You will see a staircase. You have to go down the staircase, turn right, then in the end, turn left. You will find in the end, you will see a sign for a restroom. Please follow that. If you're still confused, you can go for that guy, Jordan, with a beer cap, okay? And the next thing we have hiring. Is anybody hiring? I am. Oh, do you want to say?
Hello, can everyone hear me? Great. Yeah, I didn't know we were going to announce the hiring part, but I am hiring at Turo for a staff security engineer, staff software engineer / security engineer. Yeah, so if anyone's curious, just reach out.
We can speak. There's another one. I think we can speak after the event. There's one in the back if anyone wanna. Okay. So next thing, after the event, we will be going to a pub. It's the Pine, really close by. If anyone interested can either raise a hand so we can load. See you want barely any hands. And it's gonna be fun. Please. So yeah. And then we have sponsors. Yeah, once again, thanks to Security Compass and Video for sponsoring this event. And the next is for today, we have Bilal Siddiqui presenting about clusterf. And I think, thank you for being here. And yeah, mic's on you.
All right, can everyone hear me? Okay, great. Yes, hello. My name is Bilal. I am presenting a framework I wrote called clusterf. I will explain exactly what it is. But before I start, I just have to clear up a few things. I am looking at my notes on my phone, so if you see me looking down, I'm not sad. I'm literally just reading my notes here. The other thing is, due to the compression of the live streaming and the screen sharing qualities, a lot of the code snippets that are in the presentation are really hard to read. I'll try my best to explain them. And then obviously I'll be sharing my presentation, the slides as well, everything, all the code, it's all on GitHub, just have a look. Cool. All right, so let's proceed. Just a little bit about me. I am a security engineer. I was a security engineer. I'm now a security engineering manager, but I still do a lot of security engineering at Turo, which is also the company that is hiring at the moment. My background is security research. So I was a security researcher at Trustwave Spider Labs for a bit. I also do a bunch of independent security research. I like to write malware. I like to develop exploits. I like to hack things. And yeah. Before that, I studied electrical engineering at Western Engineering. I don't know if anyone here from Western? Nope. All good. If you're curious about what I write and what I develop, there's my website. You can also check out my GitHub. I also recently discovered a vulnerability in Apple, in macOS, which was pretty cool. I mean, they gave it a high severity vuln and a bounty, which is very nice. Before I continue, I just wanted to get a kind of a pulse check here. How many of us are familiar, or at least aware of what a container is? Awesome, great. And how many of us are familiar with what a cluster is? Surprisingly, a little less than containers, which is very interesting, but they relate to each other quite nicely. So this is a diagram. Funny enough, there's no real diagram, architectural diagram of what a container is on the internet, depending on who creates it. So I went to Claude and I was like, hey, why don't you create me a detailed description of what a container looks like? And this is what it gave me. And I was like, this is no one would ever read this. But some things to note here, and I'll just touch on a few. So containers are different from virtual machines. I think most of us know that. They're different because they're kernel level processes, and they're kernel level process isolation, and they use something called namespaces, which are just logical boundaries. So Docker, for example, it uses existing Linux primitives like truth jails, and those evolved into mount namespaces, those evolved into C groups, which added resource limits, network namespaces, which gave you IP stacks. A container basically just shares the host kernel. So it's the same syscall interface, it's the same vulnerability surface, and it's the same scheduler. And as you may have guessed, modern applications all use containers all the time. The issue is they don't run single containers. So some people here are familiar with containers. Like I said, the concept goes back to C groups and namespaces in the kernel. So like I said, a container is just process isolation. You basically just get your own file system, you get your own network stack, you get your own resource limits. You can ship an application with its dependencies that run it anywhere. So I don't know how many of us remember the it runs on my machine trend. There used to be, it's an old thing. No one says that anymore. Like it should run everywhere all the time. So we run into some issues here, right? So how do we define a container? One container, an app runs in a container, uses either Docker or containerd, which is the container runtime. One container is one process per service. Modern apps, as you may have guessed, are hundreds of apps and thousands of apps, which means thousands of containers. So what happens if a container crashes, or if a container needs to scale, or if it needs networking, or if it needs storage? This is where we enter the orchestration. This is where how Kubernetes was introduced. How many of us are familiar with Kubernetes? Okay, good, great. The thing to remember is Kubernetes is not the only container orchestrator. There's quite a few. There's Docker Swarm, there's Nomad, there's Mesos, but it won the market because it uses a very powerful declarative API that basically abstracts your infrastructure. So you basically describe what you want, like I want 3 replicas of this service, and Kubernetes makes it happen. You can do this on AWS, GCP, whatever cloud you're on, your laptop, bare metal, all. I thought it'd be fun to share one of our production clusters. So this is, I actually have someone from Turo here, and I'm sure he'll verify that this is not too sensitive information because you don't even know what you're looking at. But this is actually one of our production clusters. It's pretty busy, and you can see there's 76 namespaces on the top left, if you look. Those are really just logical groupings of resources, and there's 24 worker nodes, which are the spokes of value. Worker nodes you can think of as like VMs that kind of run containerized apps, and there are a bunch of pods. I'll get into what a node and a pod is in a bit, but basically the pod is like the atomic unit in a cluster. It's the smallest possible unit you can have. This is something we call a radial view. Each spoke is a node, like I said. The green pods are all healthy, and you can see on the left legend, which tells you the CPU usage, the memory, the storage, which pod's in a critical state, which pod's in a warning state, etc. You can't see the numbers here, but each node is running more than 25 pods. That's pretty normal for production. And Turo is not even that big an app, you know, like there's apps that need to be running hundreds of pods. Every pod that you see here is a potential attack surface. So we're looking at 24 pods, 24 nodes in this visualization, but the cluster can have more, right? Some are pending, some are in maintenance. Each node runs around 20 to 30 pods. So that's 500 pods in this cluster alone. And we have many clusters. As you can imagine, most organizations run at least a prod cluster, a staging cluster, a development cluster, internal tooling, cloud services, data engineering workloads, all kinds, different regions for latency, different clusters for compliance boundaries, depending on where you are in the world. Eventually, you're talking about thousands of pods.
He crashed. Can you join again?
Yeah. So, what was that? So as I said here, each pod is running a service, and each service needs to talk to other services, as you can imagine. So databases, caches, message queues, external APIs. If there's any backend engineers here that understand what I'm saying. Each pod also has network policies, or doesn't. That can also be a problem, but each pod definitely has RBAC permissions to the Kubernetes API. So with each pod, you want to be able to mount secrets, you want to be able to mount config maps, et cetera, et cetera. The issue becomes the attack surface here isn't linear, it's combinatorial, so it all multiplies and cascades across the stack. That quickly becomes a very serious issue for security teams at very dynamic companies with a lot of clusters. The other thing is, this stuff changes a lot. So deployments can happen multiple times a day. Services can scale up and down, pods move between nodes. The cluster state here will be different in and out, right? So traditional security tools that we've been using that rely on static config audits, they just don't keep up. And you need like runtime visibility, you need dynamic policy enforcement. This is the engineering challenge that I have. So I said I'd talk about the cluster architecture. And here's a little overview. You can see this on the Kubernetes documentation as well. This is where I got the images from, actually. So on the left here is a node, and on the right is the structure of pods. So I think I mentioned that pods always run on nodes, and a node is a worker machine, right, in Kubernetes. It can be a VM or a physical machine, so depending on the cluster. Each node is managed by something called a control plane, and I'll talk a little bit more about that. But a node can have multiple pods, as you can see, and the control plane basically automatically handles scheduling the pods across the nodes in the cluster. The control plane's automatic scheduling is what makes it powerful, and that's what it takes into account whatever the available resources are. And I think I mentioned also pods being the atomic unit in the cluster. So whenever you create a deployment in Kubernetes, that deployment creates pods with containers inside them, as opposed to creating containers directly. And each pod is tied to the node where it's scheduled. This is the control plane. So everything in a cluster goes through something called a control plane. You can think of the control plane as basically an API server. So if you've run kubectl, which is a quick and easy way to interact with Kubernetes clusters, it hits the control plane, it hits the API server. When a pod crashes, the kubelet on that pod basically reports to the API server. When the scheduler decides like where to place a pod, it also has to contact the API server. The API server is backed by something called etcd. You can see it down here. etcd is basically distributed key value store. This is like the single source of truth that we use. So every object in Kubernetes, the pods, the services, secrets are a big one, RBAC policies, they're all stored in etcd. So if etcd gets compromised, the whole cluster is screwed. The scheduler also watches for pods that need placement. So it looks at resource requests. We call like node affinity rules, taints and tolerations. Basically, a taint is like if you want to have multiple pods or nodes, you basically define one like master, and it just sort of percolates throughout the cluster. The controller manager here, the CM, and there's a little legend here as well, which you can see. The CM is basically a collection of control loops. So the deployment controller basically makes sure that you have the right number of replicas. This is important because you don't want clusters sort of competing for resources. So all of this gets very hairy, and that's why there's entire organizations and teams and conferences that are dedicated to like how can we deploy our applications safe. I'm not going to go too much about this. I could, but so we'll just move into cluster security and what it is. What is the risk that we may face in dealing with clusters, right? So clearly from everything I've said, I think it's a little obvious that Kubernetes security matters. I'm not sure why, but it matters. And it doesn't matter in a kind of compliance checkbox. Like what services are running in these pods? What happens if they're compromised? How do they get compromised? You know, the cluster I showed you earlier, that has payment processing services. So those handle credit card transactions, ACH transfers, refunds. They need payment tokens, financials, basically connections to payment processors like Stripe. A compromised payment service, then you can exfiltrate basically whatever you want. There's also authentication services. You know, these issue jobs, JSON web tokens, they manage sessions, they verify identities. So as a red teamer, I don't know how many red teamers we have here, but it's pretty trivial to forge tokens for any user if you can pop the authentication service. And then you can just escalate your privilege or bypass it very easily. Another one is CI/CD pipelines. These are very, I'm sure people here are aware of supply chain security. CI/CD pipelines are the new sort of wave of attacks that some of you may have seen. Compromising GitHub Actions, for example, or Jenkins pipelines. Because they access tokens en masse, it's very easy to trigger a race condition and just scoop up a token from the logs or while it's trying to process the next. Yeah, so all of these things require credentials. They need to perform deploys to prod, so they need those access to credentials and container registry. You know, an attacker can basically leverage that pipeline and push dirty container images. I can modify a deployment manifest, what have you. So there's risk. With this risk, I think for me, I really wanted to identify a gap, like what is the risk and what is our visibility and what is our capability. So a lot of security tools and security methodologies come from attackers. And the blue team industry does their part, the red team industry does their part. And this is a purple team kind of talk, which is I'm writing attacks so I can help defend myself, the employees of the company, or our property, et cetera, et cetera. But what is the gap here that we're trying to identify, right? So I mentioned legacy security tools. I've here written a bunch of assumptions and the reality. And maybe someone can contribute during questions and answers to see what you found in your field. So, but basically, legacy security tools, they're kind of built for a different world. If you think about it, most of them assume a static infrastructure, a kind of fixed network perimeter boundary, long-lived hosts. Kubernetes doesn't really apply to any of them because if you have a host-based agent, for example, like an EDR or an antivirus, they're designed to run on a server that lives for months or years, right? But in a K8s pod, that might live for 5 minutes, maybe 10. So by the time the agent detects something and reports it, the pod is gone. And when a new pod comes in, there's a clean slate. There's no detection state, there's no memory for it. Same thing with the clear boundary. Firewalls at the edge, IDS, IPS monitoring, north-south traffic, we've all heard these terms. That only works with clear network boundaries. Everything inside is trusted and everything outside is not trusted. Kubernetes does not have a perimeter. There's no traditional perimeter that you can think of. Every pod can talk to every other pod by default. So this is how east-west traffic can start, pod-to-pod communication. How do we control that? How do we see what's happening? Config audits. YAMLs, sure. Okay, you can scan the YAML for vulnerability. But that's only if the manifest has a security issue. It won't tell you actually what's running at runtime. You know, we can override those configs with kubectl, we can deploy them via Helm. They can exec into a pod, modify it. A static scan is just a snapshot. So how do we detect cluster security, right? Because that is a big part of it. Is all this stuff is going on, what do we detect? We use Wiz at Turo. Prior to that, we used Lacework, which just wasn't able to keep up with what we needed. So I'll talk a little bit about how we deploy Wiz in our infrastructure, and it's very by design how we deploy this. Wiz is basically the primary detection vector in our cloud. The entire deployment of it is three components. You have the sensor, you have the admission controller, and you have an audit log. The sensor is something called daemon set, which basically means one pod runs up every node in the cluster. Yeah, it's deployed as a privileged container because it needs to inspect the host file system. So you have a container, you need a sensor on it. It needs to modify, and not modify, it's a read-only sensor, but it needs to observe the file system and the network stack on a very precise level to see what are the read-write operations happening. And it's very quick. So we need to also access the kernel. You can see it needs to process, it needs access to process execution events. It uses something called eBPF hooks. I'm not sure how many people here have heard of eBPF. It's pretty nifty type of technology. It's called Berkeley Packet Filter. It also needs to monitor network connections. It needs to monitor file access patterns, metadata, et cetera, et cetera. The admission controller is basically a validated webhook. It's in the name, it controls admission. So when you deploy a pod, Kate calls this webhook before allowing the deployment. So it checks, is this image from an approved registry? Does it have no CVEs? Is the security context acceptable? Does it violate any policies? Finally, you have something called the audit log collector. Again, self-explanatory. It records every API call to the API server. So who created what pod, who accessed which secret, when, for how long, who escalated privileges. The reason I'm explaining this is when we run our attack sim and I go through the design philosophy of it, I want to trigger detections in all three layers, right? So the sensor should see a malicious process execution, the audit log should see the service account token theft, and if we try to deploy a malicious pod via the API, the admission controller should be able to block. Any questions? Before I go through the code, there is going to be a lot of code, and I really apologize if it's not readable. I'll do my best to explain it. I'm just going to go through the attack philosophy or the design philosophy behind the attack. The thing with modern attackers and modern tools and modern technologies is you can't just throw random exploits at the cluster and call it a day. It needs to be very realistic, it needs to be repeatable and comprehensive, because while this is a fun experiment for me, this also needs to be resilient in production, and it needs to be enterprise grade because other people depend on the result of these tests. So everything that you'll see in this simulation is something real attackers or I have used. You know, I mentioned some threat actors here like Team TNT, Siloscape. You know, Siloscape had a great container escape chain that actually got recently patched. They also had amazing like cryptomining campaigns. It cost companies a lot of money to fix that, and you know, it's not great if a good attacker actually compromised a pod of your cluster. These are some of the techniques they use. The other thing is the attack basically runs as a Kate's pod itself. So you deploy it, it executes a full attack chain, it logs everything, it terminates. You can run it in a CI/CD pipeline, you can run it on schedule. If you've just pushed a major cluster config change, you can run the attack sim as well. It's deterministic, it always has the same inputs. Hopefully it will always have the same outputs. but it's supposed to be robust. Talking more about the attack chain, I wanted to hit every layer of the kill chain. So for initial access, there's token theft, credential discovery, obviously malicious processes, cryptomining, process hiding, container escape, et cetera, et cetera. There's a lot of stuff here. Hopefully I can get through all of it, but yeah, let's proceed. How do I build this? This is a very crude diagram of the architecture of clusterfuck. Basically, you have the attacker on the left, that's the SIM pod, and on the right, you have the payload server. The SIM pod is where all the attacks run. So in the simplest form, and the code is on GitHub, so you can have a look at it, fork it, whatever you want. But in the simplest form, you want to simulate container escape. So you can set the privilege flag to true, you can give it some capabilities. For example, you want to mount the file system at host. I've given it some network capabilities. I'll go into more detail about why I made those decisions in a bit. But the pod is built off an Ubuntu image. It runs this dropper script called dropper.sh, and the dropper basically connects to the payload server. The payload server drops the payloads inside the SIM pod, and then it runs a script called run.sh, which runs the attack. The payload server is pretty simple. It's just a C2 server. If you can think of it as like a simple Python HTTP server. It uses a very slim Python 3.9 image. You could basically host it anywhere. For this sim, I hosted it in another cluster, but you can even host it on ngrok or wherever, any kind of machine, just to see what the egress is from the cluster that you're pen testing. Some of the things it hosts are an XM rig binary, so that's a cryptominer. It hosts a couple of rootkits. One I wrote was the eBPF rootkit. I'll talk a little bit about that. Also hosts an LD preload rootkit, port scanners, AWS token stealing, a whole bunch of stuff. So this is the Docker file for the SIM pod. Pretty basic, I think. There is some environment variables. You can see there's a payload server, there's a credential path, miner duration, so for how long to run the miner. It copies something called sim.tar. So I basically tarballed all the payloads into a sim.tar. It just preserves permissions that way. So I don't have to worry about having it not execute. Yeah, so all the attack tools are packaged in that. And then this Docker file gets deployed by manifest. Similarly, in the payload server, you have the base image, you have where the HTTP server is. You really can't see. Okay. Yeah, you have the HTTP port here. You have a shell port. The shell ports are for reverse shells. So once the SIM pod is almost done running, just for fun, I set up some reverse shells to see if that triggered detection. You can also see a netcat listener somewhere, some kind of dummy AWS credentials, yada yada. This here is called the attack sim deploy YAML. These are called manifests. So a Kubernetes cluster basically uses a container image and it translates those into manifests. So when you're ready to deploy a cluster, it basically reads this YAML, which is just a set of instructions. You can see that okay, we're going to fire up a cluster, we're going to set these values, yada, yada, yada. It uses that Docker image, which you push to either Docker or wherever, and fire up the cluster. Same thing with the payload server, does the same thing. Just want to mention that these are unprivileged pods, and it's a cluster IP service that exposes a few ports. You can use those for HTTP connection. Question?
Sorry.
Yeah.
I'm trying to imagine, like, is the payload like essentially like server like where you like sorry, I'm just trying to imagine like the purpose for the payload pod. Like is that like simulating a compromised pod or like a pod that talks to other services or other pods to compromise them? Like trying to understand.
Yeah, no, that's a great question. Originally, it was just a C2 server, so command and control server that I deployed on ngrok, which was just, I just needed somewhere to fetch the payloads from. I wanted to see if a pod could actually connect to an outside domain. And, it basically simulates compromise. I then tried to take another step further, is like, is it possible for someone to deploy a C2 framework on our clusters as well? So that's the purpose of the payload server here. It sits on a different cluster. And so basically a cluster to cluster communication, but really you can host it anywhere. You can host it on your machine. It doesn't have to be in a Kubernetes cluster. It can basically just be a server, Python server as well. It has one role, which is to serve the payloads to the SIM pod, receive the exfiltrations, and maybe spawn a reverse shell so that I can talk. It's just to see when you set up a CSPM at a company, if you're in charge of that at all, you want to test out what it can detect, right? And these are some of the things that I wanted to test out. Like, can you detect if a machine starts downloading stuff from another machine? Is that possible? It can be. So yeah. Does that answer your question? Yeah. This is the XMRig crypto mining config. This basically tells the SIM pod how to run.
Can you speak a bit louder?
Yeah, sure. Oh, can no one hear me until now?
No, it's on the live stream.
Okay, got it. Yeah, so this is the crypto mining config. Basically tells the computer or the machine, hey, this is how we're gonna configure our crypto miner. There's a wallet address. Connect to NiceHash. I don't know if people here ever mine crypto, but that used to be a thing. There's wallet address there, CPU config, huge pages. Basically, you want to be as greedy as possible with the resources to just slobber the cluster and see how much you can squeeze out. I also added some different algorithms in there, Monero, Kryptonite, et cetera, et cetera. I think Monero had an ASIC resistant algorithm. Loud? Oh, okay, yeah.
Yeah, just a question about, you said they try to make it as heavy as possible.
Mm-hmm.
Wouldn't that be against defense evasion? Because you'll get detected that fairly easily, right?
Yeah.
Because it's a heavier process running in terms of this cryptomining.
Absolutely agree. So here's the thing, we're not really attackers, right? We're chaos engineering our simulation or our CSPM. And there's a reason for this. Depending on your flavor of red teaming, you can either have a serial execution of these steps and see which one gets triggered in a line, or you can have a parallel execution. Ideally, yes, you want to have it very sneaky. You don't want to maximally squeeze the resources of the CPU compromise. But for this, I wanted to see what is the threshold. So I really just kept pushing the limit and saw like, oh, can it find out at like 1 CPU, 2 CPU for like how many does it need?
So is the config dynamic in the sense that it changes, or did you tinker and find a...
Yeah, I have to tinker a lot.
Okay.
I wish it was dynamic. Yeah, maybe that's a V2 thing.
That's the thing.
Yeah, no problem. Yeah, so this is the dropper script that I mentioned earlier. It's a very small bash script, sorry. It basically downloads the payloads and it executes the main attack script, run.sh. First, you want to check the connectivity, like can it actually connect to the payload server? Because of how Kubernetes networking works, the payload server pod might not be ready yet. Again, this is only if you're deploying the payload server as a pod itself. Or DNS could also not have propagated, which is always an issue. So originally my dropper was failing, it was 404ing, but the server was responding, but it needed an index.html. So basically I had to change it to accept any HTTP code. Yeah, and once the connectivity is confirmed, it downloads the payload archive, the tarball I mentioned earlier. that contains all the binaries. You can see them here. And it preserves the permissions. And yeah, it extracts to temp/payloads, which is not a very creative name for a directory, but it works. And yeah, this is all it does. I'm going to go through now run.sh. This is the part where I feel like the code is not readable because it is a lot of code, but I will try to explain it as best as I can. If you have questions, don't hesitate to ask. And I think you mentioned in the back, like defensive agent and all that. I made this a serial execution script precisely because with parallel execution, it's hard to figure out what failed and what didn't. And so I wanted a very like clunky, like amateurish, like step 1, step 2, step 3 kind of sequential script, just for me to see if it works. Obviously, a real threat actor would never do this, but it's a good way to think of how to detect attacks. There's around 10 stages. Some of these stages can be blended in with others, or you can add more. But on the surface, it's very straightforward. There's a case token theft. It does a credential sweep as well. So any kind of AWS credentials that are stored in configs, environment variables, etc. So it's a very basic port scan. It then does some process hiding using an LD preload binary and the eBPF binary that I wrote. It does a container escape. It does AWS enumeration. So API calls with stolen credentials, sets up a reverse shell, kicks off the crypto mining, and then does some defense evasion. So like file masking, masquerading as different files. There was a Python crypto miner in there, but it kind of stopped working. So I shouldn't have included it here, but originally that was the plan. And then anti-forensics, it basically just nukes the pod. There's very little forensic evidence. So for this, I'm basically just setting up the run script. There's some colors there up here. That's just so I can follow the output. But basically the tool storage path is very important. So it tries user sbin first. It looks for like system binaries there. It falls back to temp or var temp if permissions are restricted. I'm trying to like blend in legitimate files here. So yeah, that's why I'm trying to access these like very popular viable locations. Same thing with the hidden storage part here. You can see, I don't know if you can see there, but that's something called like, it's like a triple dot directory method. I don't know how many of us heard of that, but you store that in tempfs, which is memory and not disk. And that survives container restarts within the pod lifecycle. So it leaves no persistent file system trace. And then obviously you see some configuration, environment variables, payload port, minor duration, etc. Oh yeah, and this is also parameterized, right? So you don't have to actually worry about certain values changing. More on the environment setup, or environment variable setup. Before you start, you definitely want to clean up whatever previous artifacts may have existed or come with the pod that you fired up. Like I said, I created a hidden storage there. It also creates the dev SHM directory, which is the hidden storage actually for the stolen data. That dev null, basically, I just wanted to suppress all the errors. The LD preload artifact, it will clean those up too. I'll get into what that is in a bit. I also wanted to change some attributes. So this CHATT or chatter tag IA flag, that removes immutable flags and append-only flags. So when you want to make a rootkit persistent, you want to remove the immutable file from a directory because you want to be making changes to it. So obviously I wanted to make changes to /etc as well as other directories. So yeah, it essentially just unlocks those directories for writing. All right, let's get into stage 1. So For me, the first stage is always trying to steal tokens. Like that is just what I really want to do. I checked applied identity for service account tokens. The service account token is basically the pod's identity credential for talking to the API server that we mentioned earlier. So every pod in Kubernetes gets a service account token. It gets mounted by the kubelet. It's not optional, like it's there. It's default behavior, and it's a JOT token, so a JSON web token that provides authentication to the API. Next, we'll check some standard mount paths. So the paths change between older and newer Kubernetes versions, so I just included both. The first hit wins, and we'll copy it to our hidden storage. You can see here, but I also just extract the first 30 characters because I don't want to leak tokens in the output. We'll want to validate those tokens. So basically use it to connect to a Kubernetes cluster, see if it works. So there's basically a line there that is not readable. There's auth, can I get pods, all namespaces. It's just going to validate the token, see if it works. And then, of course, you're going to exfiltrate to the C2 server. Again, very hard to read, but after stealing the Kubernetes token, you want to pivot to finding credentials for other systems. So this is about lateral movement beyond the cluster. I'm going to sweep like 6 common credential locations, AWS credentials, because devs often bake AWS credentials directly into the cluster. Are all the executed task functions selected to be called or not? Good question. No, not as of this moment. This is a packaged attack simulation, so it runs serially. That's actually a good idea. You can probably just run specific attacks if you want to test specific attacks. You can probably just modify that with a flag, I would imagine. Yeah, so I'll continue. So AWS credentials, they can also be left over from local development if someone was using that cluster for development. There's also the Kubernetes config, so kube.config. If this container manages other clusters, it will potentially have cluster admin credentials. There's also DB configs in there. Those are often mounted as config maps or they're directly in the image. And then obviously it looks for more environment variables. Once it does that, it tries to validate. So it'll basically mount those AWS access keys and see if we can assume a role, like an AWS role, because a lot of credentials, a lot of access keys are tied to specific IAM roles. Yeah, so that's basically what this is trying to do. It mounts the AWS role, it mounts the AWS access keys, and sweeps for credentials, and then it just outputs whatever it's found. I'll show you a demo of this as well. It's not just code. This is a port scanner. It's very simple. I wrote it. It's like 30 lines or something. It works. It'll just find out which ports are open. You already know as an attacker which ports are open if you're developing this, but it's always nice to get that extra confirmation. And obviously, we want to set up a reverse shell later on, so it's good information. So this is the process hiding stage. I would say this is probably the most sophisticated stage because it uses something called, it uses 2 rootkits. One is an LD preload rootkit that I found floating around. I think someone I know might have had something to do with it, but it's really cool. And the other is an eBPF rootkit that I wrote. And the LD preload rootkit is a user space rootkit, and the eBPF is a kernel level. But they're both designed to hide malicious processes. So any kind of system monitoring and defenders, you want to hide those processes, right? So who here knows what LD preload is? I can give some fun facts about it. No one? Oh, he knows what, oh, wow, nice. What is it? I'm kidding. So LD preload, that's something called a dynamic linker. It allows you to specify shared files to load before all others. So you configure that via etc/ld.so.preload. That is a privileged file read. That file is read by every dynamically linked library at startup. So attackers use this to hijack system calls like read, adder, stat, or open to hide processes, files, or network connections. So for this, I basically wanted to remove those immutable flags that I mentioned. So there's no more file immutability, meaning you can change it, you can write it to it. Then you can deploy it, and you copy our shared library or the malicious shared library to a system library path. So basically, you're masquerading as a legitimate library. And then I make it persistent with the plus I flag.
Quick question.
Yeah.
Is this running within the ephemeral storage of the container, or is this meant to be executed after you've done it in some host?
This is prior to container escape.
So you're putting a rootkit inside the container itself?
Yeah.
Okay, so this is like a container that you've compromised.
Yeah.
You're hoping it's going to restart.
Yes, yes. So these attacks don't strictly relate to each other. They're mostly, it's like a graph, and I just wanted to see which attack gets the most like impact. But yeah, of course, if you have compromised a container, it might not need to be escaped. If it's a container that is often used, you might just want to have a rootkit in there. You might not need an escape. In some cases, you might want to escape and not have a rootkit. Yeah, this is also pretty hard to read. But this is just a little bit more on the eBPF rootkit. There is the assembly for the rootkit itself. Talk a little bit about eBPF now, which I really am quite a fan of. It's a newish kernel technology. It allows you to run a sandbox program in the kernel without changing the source code or loading any kernel modules. So originally it was designed for network packet filtering, which is kind of how it got its name, Berkeley Packet Filter. Now a lot of sensors use it for performance monitoring, enhancing security, network visibility, et cetera, et cetera. So old school rootkits needed kernel modules, so .ko files, or required you to patch the kernel directly. The eBPF technology, it provides like a kernel-like interface that attackers can exploit. So you can attach programs to kernel probes like kprobe, tracepoint, raw tracepoint. You can hook syscalls before they re-enter user space, so in between the kernel and the user space itself. And you can filter or modify what processes see in the kernel itself. So if there's a sensor on the kernel and you want to try and trick it, you basically deploy it as an eBPF rootkit, and it thinks you're an eBPF program because you're doing stuff that an eBPF module would normally do. So there's a little bit more. There's actually a reference here. If you guys are interested in how I wrote this, feel free to click the link when you get the presentation, and I'll talk a little bit more about exactly all the functions inside the rootkit. So this is the container escape stage. Quite a few advancements have been made in container escapes, and they get patched very quickly nowadays. But this is a very generic one. I basically wanted to break out of the container environment to access the host system. What are you escaping from, right? That's the question. Like, what is a container escape? So as I mentioned earlier, a container uses the Linux kernel namespace to provide isolation, like the PID namespace, the mount namespace, et cetera, but those aren't security boundaries. They're just process isolation primitives. If you have the right permissions, you can break out. So those boundaries basically collapse, and you can access the host path. In this case, the manifest mounts the entire host's file system at host inside the container. any good security tool should be able to detect this too. It's like, it's a very blatant disregard for security. My point being, you shouldn't be able to deploy a container like this in a production environment. So if you have a security tool and it wasn't able to detect this, it's not good. So now, after the container escape, I just wanted to test out a bunch of the AWS calls, like, hey, could I use these tokens? It's just a validation stage. So if you've captured tokens and if the container has AWS CLI on it, hopefully it does, you can just run these very generic AWS commands and you should get something good. Reverse shells, this part isn't great. Like, it's not super sexy to talk about. It's just a reverse shell. There's a Python reverse shell, a netcat reverse shell, and a bash reverse shell. It's very generic, but again, a security tool should not be allowed to set up a reverse shell in. And cryptomining, I think I mentioned this earlier as well. Evasion, I had fun with this one. It's actually a pretty nifty trick I learned a couple of years ago, and it still works. But basically, if you reverse the string of etc/shadow and then symlink it to another file, you can read that file. And security tools don't seem to understand that you can do that. But it's a pretty old trick. I'm surprised it still works. But yeah, it's a very simple command. Rev wodas CTE, which is etc shadow reversed, symlink it, and then read it. Very easy. I also wanted to disguise the cat command. So if I want to run the cat command on a bunch of stuff, I don't want the security tool to be like, hey, this person is running the cat command on all these files. So why can't I disguise it as different binary? You can do that. And finally, anti-forensics. Yeah, just mute it. Mute the logs. There's some other stuff here you can try. You can stop audit D, you can clear the kernel ring buffer, you can modify timestamps, whatever. So I'm just gonna show you a video of how it runs. I didn't trust the demo gods here to do a live demo, so I apologize, because it is fun to see it in real life, but I think this should work. So before I play it, you'll basically see me build the image for the containers, push it, and then deploy the pods, and then run the attack. So I'm building the image there. That's for the payload server. Once that's built, I will also, yeah, I'm applying the AWS credentials manifest. So those are some sealed secrets. So secrets are sealed either by Bitnami or they're encrypted in some fashion, and then they're sort of injected into the pod. Here, I'm going to run the payload server. Yes, so it runs. Those are listening on those ports. And then I'm going to run the SIM pod, which is the attack SIM itself. And the attack is over super quickly. That's the other thing. Like, it takes like less than 3 seconds to finish running. Yeah, so it's already finished running. But I want to see if I can get these logs for, like, you know, preservation purposes, if I want to refer like which step failed. So I'm going to basically look at the logs, the full logs. Yeah, you can see the LD preload detection window is completed, the eBPF rootkit was deployed, yada yada, container escape, all that jazz. Cool. And I think the next one. So you run this and then what, right? Like, what happens? Well, hopefully your security tool picked up at least one of these things. If it didn't, I don't know, because I'm not an actual threat actor, so this was very trivial for me to do. This is totally unreadable, but this is basically my other marks of this. So I had several versions of this attack. Depending on what it did, there was a lot more dumping of files, a lot more modifications. I'd be happy to talk about it after the talk. So what does this look like on the detection side? This is Wiz. I'll show you all the detections that it found. It actually found all of them, which is great. There I'm filtering by the namespace, so I created my own namespace for this. There's around 110 detections. Some of these are duplicates. That might be because of how many times I ran the attack. But Wiz shows you a very fancy process tree. It tells you exactly what was run at which layer, what command was run. Also, I'm not shilling for Wiz, it's just a tool we have to use. This is great also, it can tell you the forensics within that cluster, or within that pod rather. I'm going to check out some other detections here. I think this is the same one, file associated with a known high severity malware. I believe that is the cryptominer. In this case, yeah, it is. Oh yeah, this is the Etsy shadow attack. Yeah, I can see like I symlinked the shadow file. I actually caught that one, which is pretty cool. There's also a fancy threat graph that it uses GraphQL to build out all these relationships within an attack, so you're not just reading a table. And you can definitely just sort of get lost in these graphs and see what was executed when, cannot follow it exactly. Very handy as a security engineer. Also very handy for the other engineers in your company to understand what's happening. Like, I don't get it. So yeah, this is the graph of the entire attack. You can see all the different actions it took. And yeah. I wonder if there's more in this video. Oh yeah, that's the www, the eBPF binary. Again, it shows you a full sort of timeline of every attack that was performed. I wanted to see how it captured my eBPF attack. And it'll be the same thread tree, but the process execution tree is a little different. And it caught it, which is great. Any questions? Yes?
What's been your experience after running this? Show it for a thing. So it goes
I can hear you. I can hear you. So your question was, what's been my experience after running this?
Specifically going from detection to prevention.
Mm-hmm.
Like you've got this, you've got, I don't know, a dozen clusters, 100 clusters. You can run this on each and see where it's going and getting these checks all land.
You know, these attacks worked, these attacks didn't. Do you have a playbook or guide that you're sending to your blue teams, your DevOps teams, whatever, saying, look, I can do this, you don't have TLS, you don't have Pepper, you don't have whatever. Like,
right.
Is there a process after we run this to remediate, basically?
First of all, it's very generous of you to assume that I have a blue team. It's just me, really. I'm red team, I'm blue team, I'm purple team. I have 2 engineers who I work with, security engineers. We do all of this. Luckily, the platform team is very game. And this is a big lift because I understand the gist of the question you're asking. Security is a hard sell, especially the platform engineers, back engineers, whatever. But we are very lucky that the platform engineers are interested and actually understand a lot of the security. So it's not too big a lift for us to push remediations. We also try not to chase CVEs. We try to knock out entire classes of vulnerabilities. So something very simple as like, hey, don't allow file system modifications of these. Like, it's just blanket rules, and we actually do something called policies as code. I don't know if anyone here has heard of that. Nothing gets deployed that violates those policies. That's it. How we define those policies, that is an ongoing that's an ongoing thing. Another question?
Are those policies part of the CI/CD base?
Sorry, I can't hear you.
Are those policies essentially part of the CI/CD?
Yep. Yes. Yeah, so nothing gets deployed. If you want to spin up a test cluster, that's fine, but even test clusters have very specific rules. But definitely, if you're going to deploy to a production cluster or any other cluster, we try to be pretty stringent with our policies.
Hi, I would like to know if you've tried running clusterf with any other security tooling, and what were the results?
Yeah, I'll be happy to say. Does anyone here work for Lacework? No? Okay, great. So I ran it on Lacework, who we were with prior to Wiz. They didn't catch any of them. They did not pick up on any detection. And I was waiting for days, basically. I'm like, maybe this was delayed. It never showed up, and I was like, okay, this is not good. This is bad. So that was one tool. A couple of my friends have used it with different degrees of success. I can't remember off the top. I think maybe it was Jupiter 1 or something. I don't remember. I don't want to mess up the name. So, but yeah, you can run it anywhere.
I was just going to ask, how resilient is it in its current state? Like, if you were to run it under something like Barracuda, because one of the commands gets blocked, it's fail-safe, or is there any improvements that you're looking to make?
Oh, I would love to make it as resilient as possible. I think for me, the trade-off was between portability and impact and strength, and you kind of have to pick like 2 or 3 of those. So it's in its current state, I would say it's not very resilient. It's been definitely, my testing committee is basically me and like a couple friends, and they've tested it on an infrastructure that's similar to mine. So again, have a look at the repo. It's not very resilient in its current state. It might break in different environments, but I'll leave that to you guys.
Just a generic question, how affordable is Wiz? Like, what's the pricing like?
Wiz is very, very expensive. They are they're a very expensive company. We negotiated long and hard with them. Luckily, Turo is a pretty small company, so they kind of took pity on us and gave us a good price. And the rest of the conversations were like, all right, we'll see in a year. See how much you're using it, so we can jack up the price. So it's also been a constant battle of like keeping our sensor workloads down, make sure we don't cross the boundary, because any opportunity they get, they're gonna come down. So I don't know if it's a long-term solution. At this point, I would say they're pretty wealthy. Hopefully we fly under the radar, but they are a very expensive company. But I hate to say it, it's a very good tool. It's a very good tool.
Are there any open source alternatives that you know of?
To Wiz? I'm sure we can build one. I don't know.
So actually, sort of follow up in the similar topic. Within Wiz, has it been the eBPF based monitor runtime protection that is catching everything?
Yeah.
Okay,
Yeah.
so somebody showed it at Falco. Like, we're about to try it ourselves. I don't know if it's good or not, but it sounds like that's probably the direction we would want to look.
Yes, definitely. I think that is I don't want to say new wave, but that is definitely the current trend of deploying eBPF sensors. They're lightweight, they're precise, and they work, and they're quick. So I think that's just a natural progression.
Follow up real quick, same topic. What is the operational overhead of running a tool like this? I saw a lot of signal in there. Like, do you need, are you basically spending half your time being a SOC watching everything come in, or are you?
Great question. Yeah, it runs hot. Wiz runs very hot, and it's expensive. So each cluster that you deploy Wiz on, obviously that costs money. Obviously that takes up resources as well. So you do have to strike a balance between like what are your crown jewels that you want to protect, and what are the ones that can kind of like go without. So we have like internal tooling clusters, for example. Those don't all have sensors on it because like we do so much like shit in there, like it's just not worth it. With regards to being a SOC, again, we're a very small security team. We do it all. We heavily rely on Terraform configurations, PagerDuty configurations, route those alerts to Slack, to PagerDuty, etc. Like it's an interesting time. Any more questions? No? Thank you. Thank you very much.
There's a question online.
Oh, I think I answered that already. Yes, you could potentially modify them, but in its current state, it won't allow you to. But it's a very easy fix. That might actually be a v1.2.
Thank you, Bilal, for the talk. And I just want to thank our sponsors, Security Contest, and also BDO. Our next event is going to be on December 11th, I think. It's going to be a joint event with Cyber Toronto, most likely virtual. So we're going to post more details on our meetup page, was Toronto chapter. Please click on the page. And also, we're going to close the doors by 8:30 p.m. So please feel free to hang out here. And after that, it's going to get on next. I think it's going to be on John and Front Street. And we appreciate how to leave up this room, and feel free to stay here until 8:30 p.m. Thank you, everyone.
Can I say one last thing? Turo and me are also looking for a staff security engineer. So if anyone is interested, I urge you to apply. Go for it. And best of luck.